Hello everyone, welcome to the lecture series on IC applications. Myself Siva Ramakrishna, Department of ECE. In this lecture we continue the discussion on applications of operational amplifier. So if you remember, in the previous sessions we discussed some applications such as we have seen integrator, non-inverting and inverting amplifiers, voltage follower we have seen, and how to use operational amplifier as adder and subtractor. So far we have seen 5 number of applications and we continue the discussion on applications. In this lecture we will focus on applications of op-amp as logarithmic amplifiers and anti-logarithmic amplifiers, as well as we also focus on differentiator and integrator. How to use operational amplifier as a differentiator and integrator. These are a few more applications of operational amplifier. So we begin with logarithmic amplifier. So we have seen how to use operational amplifier as inverting, how to use the op-amp as, that is, inverting amplifier, as well as non-inverting amplifier. We have seen both inverting as well as non-inverting amplifiers. Also the adder and subtractor. In all these basic applications, we try to find the relation between output and input. We try to find the relation between output voltage as well as input voltage. How the output and input are related, in what way, in what manner they are connected, how we express the output voltage in terms of the input voltage. Right, if you remember the adder circuit, we applied input to both inverting as well as non-inverting terminals, saying V1 and V2. V1 and V2 are two inputs applied to the operational amplifier. So we express the output in terms of sum of both the inputs. That is, the output voltage is defined as sum of both inputs, V1 and V2, in the case of added circuit. Similarly, we express the output voltage as V0 is equals to the difference between the two inputs, that is V1 and V2. So what we said, V1 minus V2. This is what the expression we obtained in the case of a subtractor. In the case of subtractor, we express the output voltage as the difference between two input voltages. Now in this case, we said it is a logarithmic amplifier. Look at the basic description of the circuit. Here we are using a diode. As a feedback element. We are using a diode as a feedback element between input port and output port. Right. So first look at the circuit configuration, how we arrange the circuit to operate as a logarithmic amplifier. Right. So giving input to the inverting terminal. We are giving input to the inverting terminal, that is Vi is the actual input. So where R1 is the source resistance, and to connect the input and output we are using a diode. Using a diode, both input terminals and output terminals are connected. So leaving the non-inverting terminal to the ground, connecting non-inverting terminal to the ground. This is the basic circuit description of logarithmic amplifier. Now we will try to find the expression for output voltage. So in all these applications, we try to find the relation between output voltage and input voltage. That is a V out and V in. How these two are related, how these two are connected, how the output voltage is expressed in terms of the input voltage. So look at the look at the circuit configuration. We have seen the circuit configuration. We introduce a diode in place of a feedback resistance RF. This is the major difference. This is the major difference between the other circuits and this logarithmic amplified circuit. So previously we have we have a feedback resistance which is connected between the output and input. So between the output port and input port, they are connected through a feedback resistance, and this is replaced by a diode. The resistance RF is replaced by a diode. That is a major difference in this particular circuit, right? So now we are going to perform the nodal analysis. We will find the nodal analysis to find the current through the diode. What is the current through this diode IF? How can we express the diode current IF? So if you look at the circuit, we aim to find the current through this diode IF. What is the current through this diode IF that we are going to determine? We are going to determine the current through the diode, so which is IF, which is expressed as IF. As you can see in the equation, so we will express the IF as IF is equals to VI by R1. IF is equals to VI by R1, and if you apply any nodal equation, we can get it as IF plus, that is IF minus VI by R1. IF minus VI by R1 is equal to 0. So we can let this as equation number 1. So here we try to define the current through the diode. So what is it? IF is equals to VI by R1. And now coming to the basic diode current equation. What is the basic diode current equation? So that is, if you remember, IF is equals to, what is IF here? IF is equals to, we can say that IS into e power VF by eta Vt. So what we can say here? The diode current equation, this is the general diode current equation. This is the general diode current equation. This is the general diode current equation. What we can define the current as IF is equals to IS into e power VF by eta Vt, where VF is the biasing voltage, and you know about the eta and as well as the Vt, right? And now by this time we have two current equations. So let us say this as equation number 2. Let us say this as equation number 2. Both talks about or represents the diode currents. So this is as per the circuit. Equation number 1 represents as per the circuit what is the diode current, and this is the general diode current equation IF. And now let us apply KVL to the complete loop, that is starting from the input to the output. Let us apply a KVL. Let us apply a KVL to the entire loop. So what we can define here, that is, so we have VF, that is especially write the KVL equation around the feedback loop, focusing only on the feedback loop as well as the output port. We can say that VF is equals to V0. So we can say that VF is equals to V0. This is what the expression we can get. So once we apply KVL, and how can we rewrite that equation? We can rewrite that as VF is equals to minus V0. So this is the third equation obtained after applying KVL to the feedback loop. That is, after applying KVL across the feedback loop, we will get VF as minus V0. Right? Now go back to the diode actual current equation. That is your second equation number 2. So substitute whatever the value we have in equation number 2. So we can redefine the diode current IF as IS into e power minus Veta by eta Vt. So where we define VF as minus V0. Clear? And now both equation 1 and equation 2 represents the same current component. That is nothing but diode current. Both represents the diode current. So definitely both are equal. Both currents are equal in general. So we can say that equating 2 and 3. So equating 2 and 1. Right? After substituting the value of VF, so whatever the equation we are getting IF, so that we can equate it to the first one. So what we will get here? In the first equation we have VI by R1. And now after substitution we have Is. Diode current is given by Is into e power minus Veta by, so what we have, eta Vt, right? So what we need to define? V0, the output voltage V0. In order to define this V0, we will apply a natural logarithm. Look at this one. Here it is power of E, right? This whole term is expressed as a power of E. To remove or to overcome this exponential term, we are going to apply a natural logarithm on both sides of this equation. Apply a natural logarithm on both sides of this equation. What we will get here? So it will be ln of, natural logarithm is expressed as ln of. So what is here? Vi by R1. So before applying, let us perform some cross multiplication. So we will left with Vi by Is into R1. Vi by Is into R1 is equals to e power minus V0 by, that is eta Vt. We have e power minus V0 by eta Vt. Now you can apply natural logarithm on both sides. So that is applying natural logarithm on both sides. What is the result here? So we left with the ln of Vi by Is into R1. So this E you will just come out of this natural logarithm. So just like ln of E base E. So what will happen? You will get it as minus V0 by eta Vt. So once again, by performing the cross multiplication, so what we will get here? We can define the output voltage. That is V0 is equals to, so what is it? V0 is equals to, so eta Vt into ln of Vi by Is into R1. So what we are getting here? The output voltage V0 is equals to, the output voltage V0 is defined as eta Vt into ln of, natural logarithm, ln of Vi by Is into R1, where Vi is the applied input voltage. Preferably this is at the inverting terminal. So you can come out of this negative sign. Since you are applying input to the inverting terminal, you can make the equation free from it, right? So this is what the logarithmic amplifier, where the output voltage is expressed as, natural logarithm of input voltage. So how can I write this equation? V0 is proportional to ln of Vi. This is what the summary we can draw out of it. So we can define the output voltage V0 as proportional to, which is proportional to natural logarithm of the input voltage. That's why this is called as a logarithmic amplifier, right? So we will go back to the circuit and we will conclude with this. We will conclude this particular logarithmic amplifier. So in this application, we want to use operational amplifier as a logarithmic amplifier. So what is the major change here? So here, this is what? RF. So we are going to replace the feedback resistance RF by a diode. That is a major difference when compared to the previous circuits. And now by performing some nodal analysis and KVL across the feedback loop, we will try to express the output voltage as natural logarithm of Vi, right? So this is what the natural logarithmic amplifier. Now we will look at the another application, which is anti-logarithmic amplifier. So what we can say, previous one is logarithmic amplifier, where the output voltage is proportional to the logarithm of input voltage, that is natural logarithm of the input voltage. And here in this case, we are going to obtain the output voltage as our output voltage is proportional to anti-logarithm of the input voltage. So look at the circuit configuration. So here the major difference is whatever the diode we use as the feedback component, that will appear at the input port, right? So this is the major difference here. So in the case of logarithmic amplifier, we place diode we place diode at the feedback loop. We place the diode at the feedback loop and the resistor at the input port. It is nothing but interchanging. It is nothing but interchanging the two components. Interchanging the diode and resistance, that will result in your anti-logarithmic amplifier. The same thing we need to perform. Nodal analysis as well as the application of the applying KVL, we will define the output voltage. How this output voltage is related to the input voltage, that we are going to determine here. So here preferably it is going to be the anti-logarithm of the input voltage, right, leaving the non-inverting terminal which is connected to the ground once again, right. Now see the nodal equation at the input section. So we know that because of this diode there will be some current. Because of this diode there will be some current, that is called the diode current. So which will be equals to, right. So nodal analysis at the input terminal, where we have inverting terminal. Input is applied to the inverting terminal. So we can write it as minus IF is minus IF plus 0 minus V0 by RF. Right, how can I express this one? So I can write it as IF is equals to, how can I write IF is equals to V0 by RF, right? And we can rewrite this one as V0 is equals to, so how can I define V0 now? V0 is equals to IF into RF. V0 is equals to IF into RF. In terms of the current and resistance, we express this output voltage, right? So this is a very basic equation, right? And now we will bring the actual diode current equation, IF. So what is IF now? IF is equals to IS into e power VF by eta bit. So this we already know. So what we are going to do, we are going to substitute the same in the output voltage equation. So we will rewrite the expression as V0 is equals to IF. What is IF now? IS into e power VF by eta Vt into RF, right? Suppose, so since it is your inverting mode, the op amp is operated in the inverting mode, the output should be expressed in terms of the negative sign. So what we will get here? So it is nothing but V0 is equals to minus RF into IF. So what is the substitution here? We are going to replace the diode current by its actual expression. We are going to replace IF by its actual expression. So it results in V0 is equals to, so what is it now? RF minus RF into, we will get it as minus RF into IS into e power VF by eta Vt we are getting, right? Now we can define the relation between VI and VF applying KVL equation at the inverting terminal with respect to the loop, with respect to the feedback loop. You will get it as VI is equals to VF. So this is the KVL expression we are writing with respect to the inverting input terminal and the feedback loop. So we know about the what is it? V0. We know about the V0. We define V0. So which is expressed in terms of VF. Now we are going to replace VF by VI. So we can rewrite this equation as minus RF into IS e power, previously it is VF, now I am writing it as VI. Because of this equation, we are replacing VF by VI, that is VI by eta Vt, right? So I can rewrite this equation as V0 is equals to minus RF into IS e power VI by eta Vt, right? So here this is the relation between output voltage and input voltage. How it is related? The output voltage is proportional to exponential of Vi. This we can call it as anti-logarithmic. This we will call it as anti-logarithmic of anti-log of Vi. Right? In this particular case, the output voltage V0 is proportional to anti-log of Vi. So that is nothing but your e power Vi, what we are going to say. So even if you apply a logarithm on both sides, you will come out of this one. And to find the expression for V0, so this is what the expression for V0. We will express it as e power V by e power Vi. These are the two applications what we have seen. One is a logarithmic amplifier and the other is an anti-logarithmic amplifier. In both these cases, we try to define the output voltage in terms of logarithmic, in terms of natural logarithmic. In the first case, that is where V0 is defined as ln of Vi. In the first case, V0 is defined as V0 is proportional to ln of Vi, and in the second application, the other application, so we have seen V0 is proportional to anti-log of Vi. This is what the application of operational amplifier. So with this we have seen logarithmic amplifier and anti-logarithmic amplifier. How to use op-amp as a logarithmic and anti-logarithmic amplifier. Now we will move to the next application, which is differentiator. So what is it now? How to use op-amp as a differentiated circuit. Another application of operational amplifier. Look at the circuit configuration. What are the major changes we introduce in this circuit? So always have a follow back, have a opinion on the previous circuit, considering the previous circuit, and now in this circuit, what is a change? What is a major change? If you observe, previously here we use a diode, and this is your resistance. The feedback component remains a resistance, and here we place a diode here. So to operate operational amplifier as a differentiator, so what is the major change here? Replace the diode by a capacitor. Replace the diode by a capacitor. That is a major change. So where the change will appear? The change will appear at the inverting terminal. At the inverting terminal of your operational amplifier, where we are giving the actual input. So leaving the non-inverting terminal to the ground, connecting non-inverting terminal to the ground. This is the circuit configuration. Very, very minor change in fact. That will allow you to operate operational amplifier as differentiator. Right? Now we will continue the analysis to determine the output voltage. So you can easily guess what could be the output voltage here. So here output voltage V0 is proportional to, it is a differentiator. So what we are going to achieve, d by dt of Vi we are going to get. We are going to define the output voltage, that is V0 is going to be expressed in terms of differentiation of your input voltage. That will be the final result or the expected output voltage expression, which is the expected output voltage expression for differentiator. So come to the analysis here. So we are going to perform the nodal analysis at the inverting terminal. So where we have a capacitor. So what we have here? So we have a capacitor at the inverting terminal. So this we are going to consider. Here is your resistor, and here we have the input, and of course it is your output. Right? Now we are going to consider the inverting terminal as well as the feedback loop. Here we are going to apply the nodal analysis. We are going to perform this. So what we can define the current through the capacitance. I want to define, or I want to express the current through the capacitance as well as the current through this resistance. So what is it now? How can you express the current through the capacitance? It is nothing but a C into C. See where C is nothing but the capacitor. the value of the capacitor, the amount of the capacitor which you have chosen. C into, so we will write it as d by dt of minus Vi. C into d by dt of minus Vi plus, what is the current through the resistor? What is the current through the feedback resistor? We will say that it is going to be the minus V0 by R, right, is equal to 0. So how can I rewrite this expression? We can write it as C into d by dt of Vi, taking minus sign at the beginning of the expression, is equals to, I can write it as V0 by R. So this is what we are getting. So if you rearrange this expression for V0, rearrange this equation for V0, what we will get now? So we can write it as V0 is equals to, by doing some cross multiplication, you can express it as V0 is equals to minus RC. By performing the cross multiplication, so we will get it as minus RC into d by dt of Vi. So very simple analysis, in fact, very simple analysis we are getting here, right? So now you can see the expression for output voltage. What is the expression for output voltage here? So which is proportional to, V0 is proportional to d by dt of Vi, right? So of course this is some constant. Actually the product of the combination of RC will set the time. RC is nothing but the time constant. So we try to express the output voltage in terms of the input voltage, which is differentiation, which is nothing but the differentiation of input, right, where RC represents the time constant. This is nothing but your differentiator. So in this application, so what we did here, the output voltage is expressed in terms of the input voltage, which is differentiation. That is V0 is proportional to d by dt of Vi, is nothing but differentiator. Now we will look at the another application, that is integrator. So how to use operational amplifier as an integrator? Look at the circuit configuration. What is a major change when compared to the previous circuit? So what we are doing here, it's a very simple change. You can notice the exchanging of the component, exchanging of the elements. So what we did here, R is replaced by C and C is replaced by R, right? Whatever the resistance we have at the inverting input terminal, right? So this is after replacing the capacitor. Here in the differentiator, in the differentiator, the input terminal is having a capacitor, and in the feedback resistance we have a resistor. In the feedback resistor we have a resistor. So this is the major change you can observe, right? So at the input terminal we have a resistor, and at the feedback terminal we have a capacitor. This is what the change we can observe. Now, so what is it integrator? What is the expected outcome? So here the output voltage V0 is going to be expressed as integration of Vi. So what we are going to say, V0 is proportional to, this time V0 is proportional to integration of Vi. In the previous case, V0 is expressed as proportional to input, that is V0 is expressed as d by dt of Vi in the differentiator, and in the integrator we are going to express V0. We are going to express V0 as, that is a proportional to Vi, which is the integration of the input voltage. Now let us carry the analysis. So same thing, determining the currents. So what we can say here, the current at the capacitor as well as the resistor. So we can define it as C into the current through the capacitor as well as the current through the capacitor will be expressed as, so you can clearly see here. So of course this is V0, this is V0 here, right, and this is Vi here. That is a current through the capacitor as well as current through the resistor. So what is the current through the capacitor now? C into d V0 by dt. V0 will appear here because the capacitor is at the feedback terminal, and current through the resistor which is at the input terminal, which is minus Vi by R, right? So with this you can define the expression for V0, as, so what we are getting here, we will get it as a CD V0, C into d by dt of V0, C into d by dt of V0 is equals to Vi by R. Now what is our focus here? We want to define the output voltage. So what is your output voltage now? So taking C to the other side, you will get it as minus Vi by RC. We will get it as minus Vi by RC, right? So, but what is the objective here? We want to determine V0. How can I express V0? I want to find V0 here. So what we can do here? Perform integration on both sides to come out of this particular differentiation. So what is the actual thing? D by dt of V0. D by dt of V0 is equals to minus Vi by RC we have. So what I am going to do? Differentiate it, right? So what will happen? Here you will get it as a V0 is equals to, you can define it as minus 1 by RC into Vi into dt, right? So in both the cases you will notice RC. You will find RC, which is the time constant. So what is the expression we are getting here? V0 is equals to minus 1 by RC integral over Vi into dt. So where RC is nothing but the time constant. So as we said, how we are going to express the output voltage this time? V0 is proportional to integration of Vi. So this is what the application. This is the application of your op-amp as an integrator. One of the application. So are nothing but filtering actions. So in general, this differentiator and integrator circuits are also popular as the filters. We will discuss when designing filters, low pass and high pass filters using operational amplifiers, right? So in this lecture, we have seen 4 applications. We have seen 4 applications of operational amplifier. What are they? First, it is going to be the logarithmic amplifier, and then it is going to be the anti-logarithmic amplifier. So we will quickly recap today's lecture. So in the first case, we said it is a logarithmic amplifier where V0 is expressed as V0 is proportional to ln of Vi. And in the case of anti-logarithmic amplifier, we express V0, that is e power Vi. So which is logarithmic and which is anti-logarithmic amplifier, right? And in the case of a differentiator, another application is nothing but a differentiator. So what we said, V0 is proportional to d by dt of Vi. Anyway, the time constant RC will do appear, right? So what is the actual thing here? So try to remember the expression for output voltage in the case of the differentiator. So what is it? Minus RC into, that is a d by dt of Vi we are getting. And the fourth application is nothing but the integrator. So what is the general expression here? It is nothing but V0 is proportional to Vi into dt, that is integration of the input voltage. So what is the standard expression we are getting? Minus 1 by RC. Minus 1 by RC integration over dt. So these are the 4 applications of operational amplifiers, right? With this we cover some major applications, and in the next class we will discuss a few more applications. If any major applications are there in the context of the operational amplifier, that we will discuss in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.